Hi, this is part 2 in the MacGyver project because nobody could come up with a better name for the project, so I'm going to stick with the MacGyver project. And I thought we'd actually power up this board, the display board that we reverse engineered in part 1, linked in up here and down below if you haven't seen it. And there are a few questions regarding like actually driving this thing, but I thought, like, does it actually work? So we don't want to go through the whole effort of actually designing a circuit to drive this thing, building it up, and then finding, oh, there's something wrong with this. That'd really ruin your day. So I thought we'd take the existing board out of here and just hook it up. I mean, we shouldn't need anything else. I mean, presumably, if we power it on, then we're going to get something on here. Shouldn't we, Mr. Assistant? Say hi.
Well, I'm Mr. Assistant.
You're Mr. Assistant.
Hooray!
Yay! Sagan's here with me.
Hello.
There he is.
Hi.
Yeah, so we're going to power this thing up. So let's have a look at this interface here, Sagan. Let's have a look. What can you see there?
You got 0 volts, 24
volts.
volts.
And I don't have no what that'd be
Minus.
that's the milliamp interface. That's the 4 to 20 milliamp current interface, I think. And 485 is RS 485. That's a really old serial protocol. It's still used though. And 12 volts, I don't think 12 volts is going to be an input. I think that might be an output. Anyway, so we've got the cable here from the case in, and you can see that, yeah, the 12 volts is this white wire here, but basically, yeah, we've got the 24 volts, positive and negative, yeah? So I think what a safe bet is just to connect up the 24 volts
And see what happens.
and see what happens. See if the magic smoke escapes. What do you think, Sagan? So up here is so that's the interface board there. And yeah, we've got 24 volts, and there's no 12 volts here. I don't see it. I'm not blind, am I, Sagan? There's no 12 volts there. There's the 4 to 20 milliamp output, but so yeah, I reckon that 12 volts is an output. So that thing, that I reckon it's an output for something else. I don't know, goes somewhere else internally maybe. So let's hook up 0 and 24 volts and see what's what. So is our power supply turned off on channel 2? No, it's not. There we go.
Okay, I'm just going to step back because I don't want to get blown up.
You're going to step back?
I don't want to get blown up.
You think the magic smoke's going to escape?
Maybe.
Sagan's not confident.
No.
He's not confident. All right. Confidence is not high. Okay, so 24 volts. So we want to program that. So Sagan, can you program that for me? He's never used it before. He's never used the Roden Schwartz power supply jobby.
Okay.
So, well, there's different channels. So this is channel 2. So this yeah, it's channel 2 up there. So it is touchy-feely screen. So we want to set the voltage to 24 volts. So
Click here.
yeah, there you go, 24 volts, not millivolts. Oh, it did. Okay, it defaulted to volts. Okay, cool. So current-wise, I reckon this whole board is pretty, like, I don't know, a couple hundred milliamps. It's already set to 2.25 amps, 250 milliamps.
Yep.
That sounds good. All right. Have we got the probes around the right way? Red goes to positive. Blue is negative. That's a weird European thing. They use blue in Europe for some reason. I don't get it. But anyway, all right. Let's power it up and see if it does anything. Okay.
Please don't blow up. Please don't blow up.
Well, the good thing is that we've current limited the power supply, Sagan, so
It won't blow up.
it's not going to do much.
Yeah.
There's not much power behind it there to actually do much. So let's. I don't think there's any indicator LEDs on there. Can you see any, Sagan? Can you see any LEDs on that board? Little surface mount LEDs or anything?
I don't see any.
I don't see any either. Nah.
So you won't know if it's powered on or...
No. We'll know by the current draw up here. So you can read that out as we power it on. Okay. Switch it on. You want to press the channel 2 button?
0.250
Yep, go.
amps.
Yeah, nothing. Zip. It's not drawing any current at all. Okay. Oh, maybe like it's got a fuse blown or something. Measure the fuse, Sagan. Let's see what we get. Yeah, that's intact. No worries. Squeeze that sucker. There we go. 0.1 ohms. Right, so our fuse is intact. So, all All right, it's not that. Why else would this not work?
Maybe the connector's faulty. Maybe we didn't plug it in properly. That's all I can think of.
Yeah.
Just
Or
looking at it.
did I? I can't remember when I tore this down. I put the board back in. Maybe I didn't connect it. Something dumb like that. I remember they had screw terminals on the bottom. Okay, so what we want to do, Sagan, is we want to buzz out. So put it on continuity mode. Yeah, there we go. Yep, buzzer. Make sure it buzzes. There we go. It buzzes. All right. We want to probe. I'll take one, and you take the other. I want to.
We're not in continuity.
Yeah, we're measuring continuity to the black wire down here.
Stick.
Yep, positive. The red one. Do the same for the red one. Yeah, you probably have to get to this side. They're pesky, those connectors. Oh, there we go.
Yep.
All right, so we're getting 24 volt. We will definitely be getting 24 volts on our board. So turn the power supply back on.
We didn't click output.
Daddy's so dumb. I'm so...
We didn't click output.
Output. Press the output button, please.
Look at that,
Hey,
24
look.
volts.
Here it is. It showed all 8s. I think you captured that on camera. It showed all 8s and then it showed all decimal. But turn it off and on again, Sagan. And
Yeah, all
shows
8.
all 8s. Geez, that's pretty bright. And 40 dB. 40 dB.
That's 40.dB. Yeah.
40 dB. I assume 40 dB is the power setting for the measurement of the ultrasonic sensor. They've got it in dB. I don't know why else you'd have dB. And we've got a flashy LED there, but that's pretty bright. That display is pretty bright. So they're running those segments at a fairly juicy current. And by the way, in the previous video, we came to the conclusion that they're probably multiplexing this, and they're probably multiplexing each individual segment. Because you can see, turn it off and on again, Sagan. Hang on.
Okay.
Yeah, go.
And on.
You can see that's a consistent brightness between having all 8s on and not having all of them on. So it looks like, I reckon, that they're actually multiplexing every single segment. So not just an individual display. So they're multiplexing, so then you would have a set amount of current in each segment, but then you've got a multiplex, 40 different segments, which is a lot. But that's how they're doing it. And as we said, they didn't have a dropper resistor, but meh, So there you go. So it works.
It's
No workers.
It's basically sending the same signal strength across each one of the segments.
Yes,
From the one energy source.
the same
It
current.
splits it, then puts it into each segment.
Yep. Well, it multiplexes it.
Multiplexes it.
Yep. So it
across
turns
each
on one
segment.
segment at a time, but it's doing it so fast. That you can't see it. But each one of those segments is turning on at least 40 times per second. At least. Let's just probe some stuff for fun. Let me find a ground point. There we go. That's a ground point. It's very convenient, so I'll hook that up to there. And we can probe around, because you don't want to hook your crocodile clip up to the pin headers, because it can short out the other pins. Trap for young players. Okay, so we've got our pin out here, and let's have a look at the clock and, the clock. Let's have a look how fast that's going. 1, 2, 3, 4. And let's have a look here, Sagan. What do we have here? We've got 5 packets here. Why do you think we've got 5 packets?
Because there's 5 digits, and each line going up and down would mean that one digit's turning on and off.
Correct.
And then, of course, there'd be different, even smaller segments inside those lines,
Yep.
which would be each one of the little
Count how
lines.
many pulses we got in one of those. One of those packets. Just maybe the bottom one's easy.
1, 2, 3, 4, 5, 6, 7, 8.
8.
8 pulses.
What a convenience. What a coincidence. How many digits have we got in each? Oh, how many segments have we got in each
8.
digit?
That's
We've
such
got
a
8.
coincidence.
What a coincidence, Sagan. That's exactly what we expect to see. And you can see they don't update this often. So, whoa, hang on. Well, there we go. Every 2 divisions, we're at 10 milliseconds per division. So how much time between each one, Sagan?
10 milliseconds. Sorry, 20 milliseconds.
20 milliseconds total. So 20 milliseconds, they turn on, they update, or they clock the information into the LED display there. No wuckers. And these, yeah, we just got ring in on the bottom. The reason we got horrible ring in down there is because of my inductive lead here. It's not great. So, yeah, it's a bit how you doing. But you can see the signal. So, no worries. So that's our clock. And then our data is the pin next to it. And it's more randomy.
Ooh,
oh, hang on. Where's the trigger level? That's all over the shop, isn't it?
That's everywhere.
Yeah. Wow. So they're really... So we can single shot capture that. If we just single shot capture it a couple of times... Oh, hang on. I've got to put it back in the middle. There we go. There we go. It'll change a few times because we've got different displays. So depending on which one we actually just happen to trigger off, it displays that. So there you have it.
That is random.
Wow. Okay, so our data's going in every 100 microseconds, because we're 50 microseconds per division, so every 100 microseconds.
We're getting data.
What did we say before on the clock?
10?
20 milliseconds,
20.
wasn't it? Every 20, it was milli or micro? It was milli.
Milli.
It was milli, wasn't it?
Yeah.
So our data's updating
Like
way more frequently.
20 times, 100 times as fast?
Wow.
Something like that.
It's almost constant. The data is almost constant, but the clock is not. The clock, if you feed in the data, it's not going to do anything unless you clock it through. Here it is down here. You can feed in all the data you want until the cows come home, but if you don't clock it through, then it doesn't go through the shift register to drive the display.
Exactly what I said.
So that's
You
interesting.
can put as much data in as you want, but you won't get out until you clock it.
Until you clock it. That is interesting. Why are they bothering to update the information like that? So there is the clock and there is your data. There it is there. So, wow.
Big difference.
They're just wasting their time.
Like, literally.
Okay, Sagan, I'm going to probe this sucker. Oh, there's our data. And there's our clock. I need you to press... Oh, hang on. Whoa.
Single.
Run stop. Yep, cool. We captured it. There we go. So, we now have a time correlated signal between there. There you go. So they're feeding in, they're doing the data-y thing there. So,
Data
there you go.
Down the bottom, clock up the top.
Data's down the bottom, clock's up the top. You can tell it's clock because it's all periodic. There you go, and you can see that they're feeding in, well, we can actually have a look here. So now, let's try and decode these displays, Sagan. One of the displays here only has, looks like one of the bits turned on. Is that correct? One of the, oh no, hang on. One. It's only got one of the segments turned on. Which display has one of the segments turned on? Surprise, surprise, that one. So that maps over to there like that. Sagan's probably not following this because he hasn't watched my previous video.
Well, actually, I was going to this morning because I do check your subscriber count.
You do? Oh, he's one. You're
Yeah,
one of my subscribers. One of my valued subscribers.
Yes.
Thank you.
I have that.
But you're not on the forum, though.
No.
No,
Because
not
I've
on
got a
the
school laptop and, like, they don't allow that sort of stuff.
Right, yeah. Anyway, I have to talk to him about that. Okay, let's see if we can correlate this. You remember in the previous video how our data shifted in over here on this chip here, okay? So that would actually, so it's got to shift in first, but it is basically the last to come out. This one with our single digit there, we just so happen to capture it when that little flashing decimal point is turned on, okay? So that one is actually where, controlled by this chip, which is where our data is first shifted in. So what happens is the first one to shift in over here has to be the last digit over here, okay? So the first data that goes in here has to be shifted all the way over to here, so that data there ends up in this chip here.
It's even colorated. U1, U2,
U3, U4, U5.
U1,
And it...
U2, U3, 3.
It directly maps over like that. And here, have we got 2 segments turned on, or is it more? It depends on, you'd have to go in here. No. So our second one, it looks like we've got 1, 2, 3, 4 digits on. So our second display, has it got 4 digits? 1, 2, 3, oh, it's digits. I keep getting the terminology confused. Segments. Segments. It's got 4 segments turned on, and that correlates perfectly with that over there, doesn't it, Sagan?
Yep.
Surprise, surprise.
What a coincidence.
Engineering's always amazing coincidences like that.
Wow.
Well done, dude. All right.
I've now learned nothing is a coincidence.
Nothing is a coincidence in engineering. That's right. Everything happens for a reason.
Call it fate, call it luck, call it karma. I believe that everything happens for a reason.
Look, there's just data going in. Data going in willy-nilly, and there's a dead period here, and they've got a little flurry of data here. What? Why? I mean, this data's useless to even generate it if you're not clocking it through. So that's, I don't know. That's just an artifact of the state machine that they're using inside. I'm sure it's the actual PLD here that makes... Would it be? I don't know. I'd have to trace it out, actually. Whether or not, I assume it's coming from the Xilinx CPLD here. That was, I think most people's theory was that it was that and not the microcontroller. So can you come up with any other reason, Sagan? Any theory why they're bothering to clock the data in here? Other than that, I just think it's just a artifact of the state machine. It just keeps doing its thing, and I don't know. Think of any other reason?
No, I've only got 2 sides.
Okay, 2 sides.
What? Side 1, the technical side of my brain says I've got absolutely no idea.
Yeah.
Side 2 of my brain says it's data running free.
Oh, data run. It's just free running data, free range data.
Yeah.
Okay, it's free range data. That's a yep. Free range data. There you go. It's probably organic. I think it's organic free range data. We'll call that. Yeah. Okay, there you go.
Got past security.
New terminology invented by Sagan. Free range data.
Organic free range data. That's good.
Terrific.
I like that one.
So there you go. The segment current, I'm not going to tap in there and try and get the... yeah, we didn't even have a series resistor, did we? So, like, I'd have to, like, bodge in a series resistor somewhere if we wanted to actually see the current consumption. I mean, the entire board, if you're interested, is taking 100 milliamps at 24 volts. Fair amount, 2.4 watts. Geez, that's, But, yeah, we don't care about the segment current. So, yeah, we do know that they're shifting in the data like that, although we haven't correlated the blanking line as well. Oh, we've got to... we need 3 hands to probe this thing to get the blanking line. Should we go to the effort, Sagan? Yeah? Probe. What?
The probe's already up.
Oh.
You have to close that up.
Okay, so all we've got really is the LED drive like that. So let's probe that. See if we can see anything. I'm going to have to do this 3 hands. Okay. There's our clock. There you go. I can do this. And pin 8. Yeah?
Yep.
Okay. Press stop. Okay, so what we've got here is all this stuff in here is just noise. It's just because we're not probing, it's just picking up just rubbish from here. So we ignore that. But it is, you can see that it's grounded down here. So this is the display period. So it's on. So it's on during this period. And then when it goes high like this is 500 millivolts per division. There you go. And then during this period, it's actually blanking. So let's go to a white... we're going to have to redo this, Sagan. Let's go out like that.
And
Hold the tongue at the right angle and go.
there we go.
Okay, hopefully we've got enough memory depth to see that. There, yep. Okay, so yeah, only during... So it blanks it. It blanks it during... the period that it's updating the display. Otherwise, you'd see all the data turning off and on, well, real quick. You probably wouldn't see it, but you get flicker on the display. So they're effectively turning that off there. So it stays on for 20 milliseconds. So it updates the display almost every 20 milliseconds. I think it's a smidge over, 21 milliseconds. Round it to 20 milliseconds, which it keeps the information on, and then it updates it. So it just updates the display every 20 milliseconds. No, if they're leaving it on all the time, then they're not multiplexing the individual segments. That would mean that they're not doing that.
Which just changes the whole perspective of this.
It does, doesn't it, Sagan? It changes everything.
Not multiplexing.
Because, so that common collector output is low, which means that, if you're getting the onesie data out here, if you're getting the ones out of your chip, which turns the segment on, then it's going to switch those on. So they're not actually multiplexing this thing. It's just nuts. And of course, they're shift registers. So once you've shifted that data in, the data's going to stay on the output here. If you feed out the ones to this out of this chip, then they're going to stay on. And as long as that common collector's low, then it's going to source current through all of those. So it looks like they're not multiplexing this thing at all. They're not doing individual segments. They're actually turning on all of the displays. But we didn't really see any brightness change, did we, Sagan? Although the eye is incredibly good at compensating for brightness changes. The eye is one of the most amazing high dynamic range things in the world. The eye is amazing. You can kind of stare at the sun, kind of, sort of. Not really. But and then you can see right down in the dark, and it gains things up, and it's really amazing. So the eye is very adaptive. I think it's got 10 orders or something of dynamic. I don't know, it's got massive dynamic range. It's got more than 40 dB. The eye has more than 40 dB of dynamic range. I can tell you that for nothing. It doesn't look like it's multiplexing that. So there you have it, Sagan.
But guess what?
What?
They are multiplexing it. From a certain point of view.
From a certain point of view. Sagan's always thrown in Star Wars references.
Oh,
yep.
It wouldn't be me.
So what they're doing is, don't recommend you drive your displays like this. So what they're relying on is the RDS on of the HC161 driver in here, because there's no dropper resistors at all. So, there is effectively inside the chip, the RDS on of the output MOSFET. They're relying on that to drop the current for each segment here. So I think they have to be driving this at a really low voltage. So let's actually have a squiz at the voltage. So we're looking at pin 2 here. It's got to be low. Actually, 1 RITX, that's one of the VCC inputs. What's pin 1? That's 12 volts, okay. They're definitely not the HC, only goes up to 6. So it's definitely got to be 3.3 or under, be my guess. Whoa, 1.95. Technically, that's actually under the minimum spec, isn't it? For a 74HC, it'll go down to 2 volts. It's actually 1.95. Oh my goodness. It's just, the poor thing. Let's actually disconnect the display, right? So it's drawing no current, and see what that voltage rail goes to. See if it's actually a solid 2 volts or whether or not it's just dropped. Yeah, there it is. They're supplying a solid 2 volts. So they're as well, I think they've deliberately tried to set it for 2 volts, which is the absolute minimum required for the 74HC series logic to work. So that's how they're getting away with this without dropper resistors and the high brightness. So I know there's people in the comments that'll go, "Oh yeah, that's pretty clever." Okay, yeah, maybe. If you really couldn't afford those dropper resistors, and you had to have a high brightness display, and so you'd rely on the RDS on of the HC output driver, the upper MOSFET in there driving it, Yeah, nah, but they're getting away with it, and that's how they're doing it. They're driving it at a fixed 2 volts. So there's got to be a 2 volt rail on here somewhere. So yeah, for this sort of like high certification environment where this thing's being used, like in potentially explosive atmospheres and stuff, they go to all the effort to like engineer cases with these O-rings and everything, and the extra penetration depth on the case and everything when they join together to stop the explosions coming out and igniting the atmosphere and all that, and all the regulations that's involved in getting that, and they drive the displays like that. Yeah, okay. Just why can't you just put the dropper resistors in? I mean, if I was like analyzing this design for certification, I don't know if it's like part of the standard. Maybe they're just not looking at that sort of thing. But I'd go, how are you limiting your current in your LEDs? Oh, you've got no current limiter? Fail. There you go, right on the chip. Yeah, 1.5, 1.95, right on the chip. So that's how they're doing it. Technically, that's under spec. So there you go. That was certainly unexpected. I expected to see a individual segment multiplex display, but I guess they've done something better that allows them to have a more, a better, clearer display, because that is pretty bright. I don't know the actual, output of that. I got no real easy way to measure that, but it is, pretty bright, even with my lab lights on here. So yeah, I'm sure that is, reasonably outdoor readable, which is what you need this thing, because it's used in an outdoor environment, and that's how they're doing it. And that's how, of course, we can do this to drive this board. We can simply have a 2 volt rail as well. Why not? Let's duplicate what they do. Although everyone will complain, oh, Dave is showing bad design practice. Well, it's not me. Just copying Banshee. So yeah, we have 2 options there. One is to do exactly the same as what they're doing, is just like shifting the data like normal, and just like have it displayed on, just update it periodically. Like they're updating every 20 milliseconds, whatever. Like you don't even have to update the display that quickly. You can just leave it on all the time. You can update it once per second or whatever. And the free range data, of course, new industry term. There it is, free range data. That's for when you send in data that can't possibly be used because you're not clocking it. So it's just free range. Or, yep, we could just drive the sucker at 2 volts. And, it's terrible, Muriel, but, I can't say I haven't done it when I was a kid, Jeez. Come on, put your dropper resistors in. But anyway, yeah, we can certainly drive this sucker at 2 volts. But then if you want to drive it from other logic, you might need like a level translator or something like that, depending on what you're doing. Oh, and I just realized that, 1 volt per division, the data is only 2 volts. I didn't actually notice that before. So whatever chip on this board is driving that, it's also running at 2 volts as well. Or is there a level translator on there? Now I have to inspect the board a bit more. This is just, this has nothing to do with the actual project. So sorry for taking, another 30 minutes, but this is just interesting. So that's the actual segment voltage that we're dropping, 1.65. I assume it's going to be, they're going to be all reasonably matched, kind of, sort of. So there you have it. That's a rather interesting part 2. So I think we'll leave it at that. Yeah, we can just drive this thing. We don't have to go, because it's more complicated to drive this thing, like multiplex each individual segment. It's much easier, from a software point of view, to actually just drive this thing the way they did it there. Much simpler. And then just, supply 2 volts and Bob's your uncle. And it looks like you can get away with it, and that's what they're doing here. And we could get away with that as well. Anyway, well, it depends. Because, we want this thing to be battery powered. So, yeah, well, that's the thing. I don't know. Maybe in another video I'm going to have to measure how much power consumption this all takes. And I won't do it in this video. I measure individual segment currents and stuff like that. So, yeah, if we do want to reuse this, it's not the best thing because... it may just draw too much battery power. If we want to have the display on all the time and power it from an internal battery, that might be troublesome. So anyway, hope you enjoyed the video, found it interesting. If you did, give it a big thumbs up. As always, comments and suggestions down below for the MacGyver project here, and I'll catch you next time.